In this demonstration of Mosca, Mosca is configured with a binaural ambisonic decoder, so you'll need to wear headphones to listen and watch this this demonstration. Mosca can spatialize three main types of audio signal: mono signals, stereo signals, and B-format signals. And these can have various origins. They can come from disk, they can be from a hardware input, or from software via jack, or they can be Supercollider synths themselves, which are registered with the Mosca instance and receive all of the data from the GUI. So I'll get to all of those. Let's start with, I'll just give a brief overview of the interface. We have here on the left-hand side a source selecting menu. You can have as many sources here as you wish, and these need to be defined. That number needs to be defined in the startup arguments for the instance. Here we have 12 selected. We also have various faders here to control various parameters of the sound, and various checkboxes here, Doppler, loop, etc. At the bottom left, we have the automation transport. That's from the automation Quark by Niels Hofmeyr. I'll explain all of that. And top right, we have other buttons for loading audio, streaming audio from disk, showing nodes, showing data, auxiliary controllers, and a method to audition a particular source, as well as to record or basically capture audio from Mosca and record that to disk. Okay, let's first of all load a mono signal, a mono sound from disk. So I've got here a short recording of a horse galloping. Let's place that on our blue disc. The blue disc represents the audible range. The grey disc at the centre, at the origin, is our listener. When sounds move beyond this disc, they become silent. But as they move further away still, any processes associated with that source, so any synths linked to that source, will be shut off, and they will turn on again as the source approaches. So that's a measure for efficiency, essentially. So you could have thousands or tens of thousands of sources, if you wished, sitting off screen and not using any resources. Okay, so let's audition our horse. It's looping, and let's give it some level. So you can see here we've got distance attenuation of the overall level. There's also some high frequency roll-off with distance. Now, we may wish now to apply some reverberation. We've got two types of reverberation controls. We have distant reverberation and local reverberation. Distant reverberation applies when the sound is distant, obviously, and close reverberation when it's close. However, in default mode, distant reverberation is a type of reverberation that's spatialized along with the source, and close reverberation comes from all directions, so it's an omnidirectional diffuse reverb. So let's listen to that. Let's first listen with distant reverberation, and to speed things up, let's put some Doppler on the horse as well. So we put an amount here and we select Doppler in this checkbox. Let's play. So you can hear that wet sound. It's now dry. And that Doppler should be apparent as well. Let's now add a little bit of close reverberation. Perhaps I should add a little bit more to hear that. Let's exaggerate that close reverberation. Now you can hear that's coming from all directions. And as it leaves us, the reverberation becomes directional in the direction of the source. There's another type of reverberation. I beg your pardon, that was actually set on A format. I'll try that again briefly. Coming back. So that should be fully, that should envelop us fully. But there's also a more correct reverberation here, A format reverberation. And that's in the internal workings of Mosca and the ATK. Well, actually, no, in Mosca, the signal is turned from a B format signal into an A format signal, and then reverberation can be applied to that. So this type of reverberation, which actually works in first order or second order, is applied to an A format representation of the source. Now, one other thing I need to mention is that the way mono sounds are spatialized in the ATK is that they are they're first turned into a B format ambisonic signal. So it starts as a mono signal and it's turned into an omnidirectional B format signal, and then it's pushed to give it an angular location. So that's what happens. So when we, for example, let's remove some of the reverberation here. We can also, we start with a fully contracted image, but we can decontract that. Let's bring it a little closer. But there's no spatial information here now. We're just listening to an omnidirectional signal. Let's recontract. That's now isolatable. We also are forgetting to mention we have a Z-axis, so we can put that horse up on high and bring it down. Let's move that away. Okay. So we have that contraction. We also have other ways, other methods when using first order ambisonics of turning our mono signal into an omnidirectional signal prior to pushing. So we have these two types here: a diffuse method and a spreading method. Let's listen to spread. It's still contracted. Let's decontract. So you can hear now we have an ambisonic signal with no real sort of spatial definition. However, the spectrum is spread across that field. It's a very different sound to the default. Let's now try diffuse, and that's another effect entirely, which doesn't really suit the horse, but may suit other sounds. Okay. Angle relates to stereo files. We'll come to that later. Rotation B format and also directivity B format. Let's have a look at live input. Let's take the horse out. And live input, you may have noticed we've got this source here, number 12. Number 12 is actually the microphone that my voice is running through. So if I'll move to source 12, you notice that hardware in is selected here. We're in audition mode, so that's how we're hearing the signal. We also have to define here the number of channels and the start bus. So this microphone is actually connected to a hardware interface on channel 17. So these buses here start at 0, so that corresponds to bus 16. So this can be, of course, shifted to the left or behind or any position. And also live signals can have Doppler applied to them. And that should be having some effect on the voice. 1, 2, 3, 4, 5. So that's working. Let's place it back. So that's how hardware we can capture either signals from hardware or from other software via jack, and these can be once again mono signals, stereo signals, or B format. Okay, we also have let's go back to our source one. We also have this option of recording. This is basically a capture of all of Mosca's output to disk. And we need to define the number of channels we wish to capture in the startup arguments of Mosca. In this case, I would have put in the value of 2 for stereo. We also have this option of placing blips at the start of the recording. That is so that we can, if we're, for example, making taking a video of a presentation, we can, at the beginning of the video, run record and have the camera record the blips via a pair of headphones, for example, or a loudspeaker. And then at a later point, we can synchronize the recording made with Mosca to the camera footage using those blips. Okay. Let's now look at B format. So we'll this time instead of loading into memory with the load button, we will use the stream audio, which is useful when dealing with larger files, in that it will stream from disk, so that the files can be of any size. I've got a recording here of Chinese Buddhist monks. So it's a larger file here that would actually do to put in memory, but we'll stream it. Okay, we'll put the monks behind us to the right, and let's loop is selected. We can put a little bit of distant reverberation, and let's select here linear intensity. So generally the sounds respond in a type of inverse square law in relation to distance, but in this case let's select a linear relationship. Okay, we'll audition the sound and we'll bring the level up a little. So in this case we've got a B format signal that's completely pushed in a particular direction. So it seems to be coming from behind us to the right. And but as it approaches us, the B format field will start to envelop the listener. So you can hear that. We can also adjust the contraction, and in the case of B format signals, that will do a crossfade between the B format and the W component. So we can listen to that. Let's contract the signal. So now we have a mono signal that behaves as any other mono signal. Let's decontract. We can also rotate the field. So now the monks appear to be behind us. So back in front. And also we have the idea of directivity, which unlike contraction, we maintain the omnidirectionality of the field. However, all of the directional information is removed, so it's essentially a mono omnidirectional signal. Here we go. So it's omnidirectional. However, there's no spatial information. Let's return. reverberation working there. Okay. Let's now have a look at the automation quark by Niels Hofmeyr. We can first of all take a snapshot. Now this little button here is the snapshot button. It's very useful for setting up for recording all settings for a particular moment in time, and this is particularly useful at the beginning of our transport, so at 0 seconds. We can, for example, take a snapshot, and that will record. Let's open up the data window here. You can see here we've got two. This particular number 12 is the microphone, so that has all of the data for the microphone represented. We also in source 1 have our Monk B format recording, and you notice that it's streamed, and we also have a linear attenuation. Loop is selected, and Doppler is on. How can that be? That's strange. Anyway, there's no Doppler now. Anyway, so that's our representation. Why was I mentioning that? I'll continue on. Let's hide that. What we want to do now, that's right. Let's say, for example, we move the transport and we mess up our values here. When we return to 0 with the transport, we will resume with the settings that we already marked. So I can either press rewind or scroll backwards, and there it is. So these values have bounced back. I'll do that again. Oh, there we go. So they've been recorded for 0 seconds. So that's useful. Let's now make a brief recording. So I've gone into record. Rotation. For the hell of it. Let's take them away. Now another thing to notice, as well as snapshots, we can also do another trick here. Let's go back to the beginning. If we wish to tweak particular various values, we go into record without moving the transport, and we can adjust those, and you'll see that's just turned red, so it's registered the movements here, and it will retain the last level, the last reading entered, so we can adjust various faders, etc., and they'll be registered there for 0 seconds. That's another method. But let's now put in a second sound, so we'll put in a horse, for example. Loop, Doppler. We're at 0 seconds, so I'll give it I think that level should be okay. Or we can do this in record if we wish. Doppler amount. Distant reverberation. Tiny bit of close reverberation. So all of that's been registered. Also registering that initial position of the source. And let's go into record and add the horse to the monks. No, I don't know about you, but I found the monks a little loud. So we'll return. We don't need to go out of record. Let's go back to source 1. We rewind. Let's drop this level down. So I'm adjusting that level in real time. And we can go back to 0. Let's also adjust the Z-axis for the horse. Just for the hell of it. Doesn't really serve any useful purpose, but okay. So there we've got 2 sources recorded. Okay. Now, the next thing I'd like to show is how we can slave this transport to an external source. So I've got Ardor sitting off to the right here. I'll drag it in. And we've got some audio here. Now, first of all let's slave the transport, and we can scrub through this Ardor's timeline here, and you'll see the Mosca's GUI and record of events following that movement. And if we wish to, we've got one track here, which has got some essentially electronic music written in, also in Supercollider. We need to define its output. So we have here Supercollider. Let's we can use tracks 1 and 2, which corresponds to buses 0 and 1. So that's where that will go. So we need to set up a third source, and in this third source we need to, as we did with the microphone, select hardware in. We need to define the number of channels. This time we have 2. And the starting bus, you'll remember I selected the output of this track to go to tracks 1 and 2, so that starts at bus 0, so we can leave that where it is. Let's take a guess at the level. Place it here. We place an initial location for our source, and we can take a snapshot. And let's see what happens. So it should be working. I don't need. Let's skip the auditioning, and let's actually try and record as well. So we'll use the transport of Ardor. Let's play. So they're entering. Let's bring in our sound, which makes absolutely no thematic sense with what we're listening to. This is stereo signal. Okay. So that's been recorded. I'll just bring in that's a fourth source, just to show you something about the angle, stereo angle. So let's audition this. It's a matchbox being shaken in front of a stereo pair of microphones. And you can hear that separation there. We can reduce the angle. So here we've got an angle of 1.05 radians. which corresponds to 60 degrees, which is a pretty standard. Let's put the loop on, play that again. We can make that mono if we go to 0. It's now a mono signal. Or we can open it out to 180 degrees, which is 3.15. Okay. All right. Now let's skip out of this entirely, and we'll have a look at Supercollider input. Oops. Okay. Let's first of all open up our Mosca help file. Just run help on the Mosca class name. Here we have the help. Now if we go down here, first of all we see the first block of code in the examples was basically used to open up our Mosca window. We also have, if we were to close this window, we need to run something to clean up any of the definitions made outside of Mosca. For example, we defined our coder in this block of code before launching Mosca, and also opened up a MIDI connection. So these two things need to be cleaned up. Just remember that. Now, here we have using Supercollider synths as input. Now we have here, let's just put that out of the way. This little class method here, print synth params. This will show us all of the parameters of the GUI that are available to synths that are registered with Mosca. I'll come to registration later. But I'll run this little block of code, and we see here in the printout, just make some space. We see here these particular, if you look at the very first value here, this is the name of the variable that can be defined within a synth and receive values from the GUI. So for example, our X, Y, and Z coordinates are called MX, MY, and MZ. Our B format angle is rot angle. Now, we're not actually recording, we're recording mainly these faders and also position, Z-axis, etc. We're not registering Doppler, loop, A format, these ones here, because it's assumed that these won't be adjusted dynamically during a recording. And that's mainly because it's very impractical to edit them. So I've disallowed their recording by automation. They could be recorded by automation, but they're not. They're actually will be recorded to disk on a once-only basis. So for every particular recording, you have to set loop, Doppler, etc. once, and that will carry for the whole recording. Can't be moved dynamically. So these you won't find in this list here. You won't find these checkboxes represented. It's more the faders. I also forgot to mention we can save our automation data with this save button. You'll see here a path that's been defined in our startup arguments for our Mosca project, and within that Mosca project we should have what do you call it? A directory called auto, where we save our auto data, and we could put in a name here of a file, test. And that will save all of our automation data to disk, and it can later be loaded. All right, returning to our let's run that again. Our values here. I'll show in this example here we have a synth, a very basic synth that's got some pulse width modulation. But basically, in its arguments here, we have an out bus, so it's just going to the directly out via bus 0, and it's got an initial frequency, and it has an X and a Y value. Now you notice that's MX and MY, So that corresponds to these two parameters here. So they'll be used to manipulate this synth via the GUI, and because we've registered, in the future we'll register this synth with the GUI. So I'll come to that. So these are our two parameters that will come from the GUI. Let's run that block, and we'll drop down. We have here two sources. Let's just do one, and I'll need to edit this quickly. Let's play around with setup for source 5. Now, first of all, any synths that you create and want to spatialize via Mosca, you will have to register with the Mosca instance. So this test Mosca is the name of our instance for this for Mosca, and we register synth. So that here, for example, in our function that's going to contain all of our synths, we've got an example here of my other synth, right? So that's the name of this synth instance when created. So we put in here my other synth, and we put in here the source. This first argument is the source. We wanted to associate it with source number 5, so we put in 5 here, and I need to adjust. We also in our for our output bus, we need to use this get Supercollider bus method to define that output bus for the synth. So that's done here. So that's selecting for output bus 5. We also need to have I'll get to registration before deregistration. So this is our function here, from here to here. We also need to have we need to register our synth, as I mentioned. So that's here. Now, what that will effectively do, whenever we make a change here in the GUI or to any fader for a particular source, that will make a set message for for whatever. For example, here we're adjusting MX and MY. There will be a set method for any synths registered for that particular source for that particular parameter. So MX and MY being manipulated. So there's set messages set out for any synth registered to that source. So that's what's happening there. So we have a registration. We also have to deregister the synth once the synth stopped playing. And the easiest way of doing that is by setting up an on-free method here for the synth instance. And we have here our Mosca instance name and our deregistration method for source 5 for my other synth. So that's happening there. Okay, the other thing that we need to do is set up a trigger. Now, this is where our encapsulating function comes in. So it's called source to play function. The trigger is related to the position of our source. And for example, if our source is within the blue disk and I press Audition, that will call the trigger, and that will call this function. If the source moves away and moves beyond the distance of a radius of 1.2, we'll call a stop function. And we've defined our stop function here, which is, in this case, is just a simple free message because we've got one sound. So we call free, and when we leave, so that's freed. And as we come back in again with our source, it will the trigger function will call our synth once again. So that's basically how it works. Let me continue editing this quickly. Okay, so we've got fives, 5 size 5s. That's all done. That should work. Okay, I'll run this. And of course, nothing will happen until we either audition or play our transport. I'll just put that away somewhere. Now, in our window, we need to, for source 5, we need to select here Supercollider in. We need to define the number of channels as well. So it's a monosynth, so I'll select 1. Let's let's see if everything's working. So I'll just place the source here in the audible range, and we'll click Audition, and let's lift the level here. That's working. So this is a really primitive model of a fly or a mosquito, and that's actually what Mosca means in Portuguese. It means a housefly. So we can hear here, it's receiving the X and Y coordinates and adjusting the pulse width of the synth. So that's getting some information from the GUI and doing something with it. For this sound to sound interesting, we need to put in Doppler. And a bit of reverb wouldn't hurt, so I'll put in some reverberation. And let's drop the level a little bit. Let's listen. So you get the idea. All right. Okay. Now, the next thing I'd like to talk about is proxies. In our help file, if we go up to the very beginning to description and then go down, we'll see we've got a subheading here called Coded Control of Mosca. Now, this lists, when we record with automation, you would think that it's recording the actual GUI elements themselves, and it certainly could. However, what I've got in between these GUI elements and the back end is a proxy, which actually behaves a lot like a GUI element. However, it's not. So when we move a GUI element, it changes the proxy, and then the proxy adjusts whatever variable needs to be adjusted in the back end. Now, this means that when we load and play an automation recording, it will play the proxies rather than the GUI. So this means that we can run Mosca without a GUI, which could be useful if you want to deploy a particular setup on a small computer and not have the overhead of the GUI. There's other reasons why you might want to do this. So because the proxy will adjust the back-end values, and if there is a GUI present, it will update the GUI element, but it doesn't need to. So so that's one reason for having a proxy. The other reason is that it's a very handy interface to adjust the GUI or the back-end via code. Now, this could be, for example, you may have a gestural interface that you wish to use to control various sources, and that can be, for example, if we have here a list of our proxies, and the first 3 here are our X coordinate, Y coordinate, and Z coordinate. So we can use these particular proxies to adjust a particular source. And these proxies are actually, it's an array of proxies. So in the case of this Mosca instance, we have 12 sources, which means we'll have 12 proxies in an array, and starting at 0, of course. Now, I mentioned before they behave a little bit like GUI elements. So in that they have a get and a set method, and also an action method. Let's have a look. So if you look down here at the bottom left, let's get a value here. let's get the x value, for example, for source 1, which is 0 in the array. So place in here value, and let's have a look at our output. So down here, let's just run that. Or let's also have a look at where, let's place source 1. So our x value presently is 0.007. X, by the way, is in the x-axis is this axis here, y is here. So let's place that up here and run it again. And now we have a value of 0.87, 6, etc. So that's how you can get a value. We can also set it, in this way. Place our value in here, 0.2, for example. But if we want to propagate that value through and affect the back end and whatever else, and also our GUI, we need to put in a value action. So let's run that. You can see that's just jumped, our little 1 has jumped from up there to here, which is where x is 0.2. So we've got that. Let's now have a look at a little example in our examples. So where is it? Here it is, coded control of Mosca. So you see here we've got a little algorithm here, which was written by someone called Will S. It's an orbit algorithm, and basically we're producing x, y, and z coordinates. Actually, the z coordinate is a copy of the y coordinate in my version of this algorithm. So let's run this. You'll see here here's our Mosca instance. Here's the X proxy, the Y proxy, the Z proxy for source 1. And we're setting and calling the action for that proxy, which will basically set the back end and also adjust the GUI. So let's run that. I should tidy up the screen really, but you can see number 1 following an orbit, wrapping around the Earth and going out to space. We've also got our z-axis in action, which is actually just copying the y-axis. But let's, I'll stop that. We've got a little while loop here, so I'll make the value for orbit false. That's stopped it. And let's load a sound. So I've got some satellite sounds here. There's a sound of the original Sputnik, recorded by Roy Welch in 1957, I think. Let's just have a listen to that. Have we got Doppler? No. Oh, you'll notice that noise there. That'll occur if I could avoid that by dechecking Doppler, adjusting, and then selecting Doppler. So we've got our Doppler working on the sound. Give it a bit more distant reverberation. Give it a 1950s sound. Okay. Let's now put the two things together. So we'll run our orbit. Let's now run our sound. You can see with the z-axis here, we're starting up on a high, and the sound should be coming over our head and then wrapping around underneath us on its return. Let's listen one more time. Okay. All right, so we're nearly done. I'll turn the orbit off. Got one more thing to show, and that's no, we've got two more things actually. We've got A format inserts. So let's have a look here. There's another example here in the I won't do now, running Mosca without a GUI, so you can try that to have Mosca running independently of the GUI. Let's have a look at our effects inserts. So this is very useful because now everyone knows that B format is an asymmetrical ambisonic format, and it's not very good to apply an effect to that signal. If we wish to apply an effect in a symmetrical way, we need to convert that signal into an A format signal, and that's easily done here. Let's, for example, let's firstly start a little synth that performs a delay on a signal. So I'll run that. So you'll notice in this next, when we create an instance of that synth, we have our Mosca instance, and we want to get a first order ambisonic insert in. And for the in bus of that synth, and for the out bus, we want to get a first order insert out bus. So basically, we're making our insert with these two methods here. Okay, so I'll run this. First of all, let's load our trusty horse. So we're looping. Let's have a listen. So that's all good there. All right, so we've got a horse. Now, did I run that insert? I don't think I did. So let's run it. It's really quite simple. Okay, let's listen again. So now we have our horse with an echo, but the echo, unlike if you were to echo the source itself and run through, make gestures, our echo will occur where the horse was. So spatially, the echo will occur where the horse was when it made that particular sound. So we'll have a spatialized echo that's independent of the current position of the horse. Let's listen. You can hear that echo wrapping around there. Okay, that's essentially it. To free the synth, to free the insert, you just simply need to free that synth. So I've done that. Oops, where's our horse? Oh, I think I need to stop it and start it again. That's curious. Look, if there's an error there, I'll check it and make sure it's fixed before this is released. I have no idea why that's not working. Anyway. No, I made a mistake. Look, you see, you have to, I clicked the wrong free. You have to actually release the insert. I'm sorry. So that's why we've lost our source altogether. Okay, so that's all good. The other thing I want to mention is that there's head tracking available. Now, if you come to our first block of code, there's information up in the description, at the end of the description, after coded control of Mosca, there's serial devices and head tracking. So here, this gives an example. It tells about two things, about use of the Arduino Uno with the Arduino 9-axis motion shield. And I forget the type of chip that uses, but it's an absolute motion detector which self-calibrates to the magnetic field of the Earth, so you can get a true and stable head tracker with that with that device, and in the Git code for Mosca, I've got that here, as well as all of the Mosca Quark stuff. We have also this Arduino head track project essentially for Arduino. So you'll need to check the Arduino documentation, but it's very easy to program the Uno with this code to run with the 9-axis motion shield. And that will produce what is it? Pitch, roll, and what is it? Heading, pitch, and roll data, basically to manipulate a B format. Sorry, a binaural field. So it's the head tracking, of course, is to be used with a binaural decoder. And if you were to have, let's have a look back at the the example code. You'll see here it's been commented out, but in this example with head tracking, you'll see that we've defined here a serial port. We've got here the address of the serial port, and that's a persistent name, which you'll need to, what's very useful to configure. I've got instructions up in the help file of how to do that in Linux. On Macintosh, you'll have to find out how to do that. So we've got that. Our device is defined here. We've also got something called an offset heading, and that relates to. I'll jump to it because I can't really run the head tracking for this video because any of my head movements will upset the imaging. I didn't. I've run it without head tracking, but I've taken a screenshot of the GUI with head tracking configured, and you can see here at the bottom right of the Mosca GUI, we've got values for heading, roll, and pitch. And these, of course, will not be static like this. They'll be jiggling around with the small movements of the head. But you'll notice here our heading value, which is the horizontal movements of the head. That's the most common movement we'll encounter. Is almost zero. It's slightly off to the negative. But that that's because I've actually put in what was it called? An offset heading adjustment of -2.6. Now, because the head tracker adjusts for magnetic north, and my computer isn't facing magnetic north, when I'm sitting here without a offset heading adjustment, my value here in heading hovers around 2.6. To make that zero, so that a sound sitting here appears to be in front of me rather than off to the side somewhere, I need to put in an offset heading value of 2.6, which is what I've done, and that adjusts this to be zero, more or less. The other reason you would use a heading offset value is if you really want to adjust your head tracker to true north. Now, there's something known as magnetic declination, and that's a correction value needed for a compass to register true north, because a compass, of course, measures magnetic north. But if you're doing any orienteering or whatever mapping activity, you want to know where true north is. And that will require an adjustment, and that adjustment isn't static. It moves everywhere in the world and actually moves with time. So up in the help file, I've got some online resources to calculate the magnetic declination for wherever you are in the world. You can put in a name of the nearest city, and that will give you a value. One last thing I forgot to mention is the auxiliary controllers. These work in relation to Supercollider input. So when you when you're recording, you can assign one of these auxiliary controllers or one of these switches to the inputs of your synth. And I'll just quickly open up the help file here. And I'll just run print synth params once again. And here you'll see the variable names. So you can put in here aux1 to 5 or aux1 check to aux5 check. And those can be used as inputs to the synths if you need additional controls.